Hello again, this is Philip Myers at PEMY Consulting. In this module, I want to go over a tool that's available on our website. This tool is a spreadsheet that will help you understand the corrosion rate issues thoroughly by playing with it and to convince you that there really is a problem with the API 653 corrosion rate model. Secondly, it can provide you with a check on the corrosion rate life that you are using in your inspections or for your company. Some inspection companies are already applying our bounded corrosion rate. I want to emphasize that we are not attempting to change anything about the way API 653 is being done. Rather, we're supplementing it by providing checks and balances on the results, which are good practice and which should be done in any case because of the problems with the corrosion rate model in API 653. This spreadsheet allows you to compare the difference between the API 653 corrosion rate and given here and the linear corrosion rate. So we want to watch these two numbers. Using these numbers, we get the API 653 interval and then the bounded corrosion rate interval. We compute this bounding factor and really a lower bound on the corrosion rate, which is based on not holing through. That's given in this column, but the purple are the two sets we want to look at as we proceed. So we have a standard model, pretty much a 1/4 inch bottom with a 10-year service life. The repair to thickness is a reasonable 200 mils. The minimum remaining thickness, the MRT, is 100. We'll start with a fairly low corrosion rate. 50 mils of corrosion in 10 years is, of course, 5 mils per year. API 653 agrees with that, and both alternatives give 20 years for a corrosion rate life. Now let's boost the depth of corrosion to 100 mils. And we see that the linear corrosion rate, of course, has gone up. It's doubled. But look at the 653 corrosion rate. It remains the same. That's because it's only a function of the repair to thickness. Except that in this case there's no difference. Both corrosion rate lives are the same, and that's because the lower bound on corrosion is still less than the linear corrosion rate. As long as it's less than the linear corrosion rate, there is no issue. The 653 methodology works. Let's now boost this up to 150 mils of corrosion. Now we see that the cell, this cell here, has turned pink. Having trouble with this marker. The cell has turned pink, 7.5 mils. That means that this is greater than the 653 corrosion rate, and the bound on corrosion should be applied. That results in the life of 13 1/3 years instead of the API 653 corrosion rate. Let's go to 200 mils of corrosion, and now we see that the lives are quite different. 20 years for API 653 and 10 years for the bounded corrosion rate method. One way to make this job of comparing the two easier is to look at this table here, which does the same thing, except that the corrosion depth is varied for you across these columns. And so you can actually see that the lower bound only kicks in when the depth of corrosion exceeds 100 mils. So the 653 corrosion rate is here, and the linear corrosion rate is here, just as we saw in the upper table. The two intervals are compared in these two rows. Okay, what we have here is 4 plots that summarize everything that we've been talking about up to this point. We have 4 plots. They are based on a repair to thickness, or a thickness after repairs as specified by API 653 of 180, 190, 200, and 210 mils. On the y-axis we have the internal inspection interval that's computed by API 653 or by the bounded corrosion rate method. And on the bottom we have the linear corrosion rate. So the red dotted line is the API 653 corrosion rate life, and notice a very striking point, and that is that regardless of what the previous corrosion was, whether it was low or high, the API 653 life is not dependent on that. The condition doesn't matter. What it depends on only is the repair to thickness, in this case 180 mils. The blue line is the bounded corrosion rate, and at this point up to 16 mils per year it does not make any difference whether the 653 method is used or the linear corrosion rate method is used. But as your repair to thickness increases, say to 210 mils, notice that now if the corrosion rate is actually, the linear corrosion rate is actually higher than 7.5 mils, you will hold through at about 27.5 years. Most people are not going out beyond 20 years, so that would be a repair to thickness of 200 mils. And what we see here is that the linear corrosion rate, if it exceeds 10 mils per year, you will hold through under the linear corrosion rate model. These plots pretty much summarize everything that we've talked to up to this point. This is fully documented in our white papers on our website. Alright, this is the final slide of the three-part API 653 corrosion rate series. In our extensive tank engineering and inspection work, we've reviewed hundreds and hundreds of inspection reports. We've seen the good, the bad, and the ugly. We've developed a spreadsheet that takes the best of them all and incorporated it. This spreadsheet's available for lease, or you can review the link to see how it works and develop your own good spreadsheet. Second point is we want to ensure that you're not in the danger zone. Basically, we want to make sure that you're considering the bounded corrosion rate so that under the linear model you don't get a hold through because of the flaws that are in API 653. And again, they only occur under unique conditions. All of this is thoroughly engineered, documented, calculated in white papers and calculations that are available on our website, www.PEMYconsulting.com. Thank you.